So now we're going to talk about vaccinations, anti-sera and anti-venoms. With vaccination, you're deliberately exposing the body or the person, or more specifically their immune system, to a particular antigen to stimulate an adaptive immune response against that antigen. Now, the aim of vaccination is to stimulate the production of memory T cells and memory B cells to provide long-term protection. Sometimes this immunity or protection is lifelong, such as is the case with the vaccine for measles. But sometimes then you might need booster shots where you get exposed to that antigen again to sort of prime the immune system. And we see that with tetanus booster shots. We also get our seasonal flu vaccine for sort of seasonal variants of influenza virus, and as well with whooping cough as well. It's been shown in more recent years that those vaccines that we get against whooping cough when we're children is insufficient for some people to provide lifelong memory, so they also need to get a booster shot. Now, with vaccination, it's usually done before the person is even exposed to a particular pathogen. And then that means, that they will have developed those memory T and B cells when they eventually are exposed to that pathogen. And those memory cells then, will mount a response that will lead to the destruction of that pathogen before any symptoms of the disease are evident. Now, vaccination is artificially acquired active immunity, and I just want everybody to be absolutely sure what vaccination is. So with vaccination, either a dead viral, a dead pathogen, or a protein subunit of a pathogen, or maybe a live pathogen, but it's diluted so that it can't cause disease, might be used in a vaccine. Or more recently, these newer generation vaccines being those messenger RNA vaccines or DNA vaccines can also be used, right? But what they're doing is they're priming the immune system, okay, to develop memory against that particular pathogen, so that on subsequent exposure to the same pathogen, the immune response is really rapid and it's really strong, and it leads to the destruction of that pathogen before any symptoms of the disease are evident. So everyone, the benefits and advantages of vaccination are absolutely massive. And if you can get the majority of a population, vaccinated against a particular pathogen, so upwards of 70%, probably more like 85%, then you will have herd immunity for protection against that pathogen. And herd immunity describes how if you have the majority of a population vaccinated, then those who for whatever reason can't be vaccinated are also protected. And that's because the spread of the pathogen from one person to another person is very unlikely. So it's not just the people who are immune because they've been vaccinated that are protected, but everybody in the community is protected. Now, mild hypersensitivity reactions can occur in people in response to a vaccine. However, anaphylaxis, remember what anaphylaxis is? It's that immediate hypersensitivity reaction that involves systemic inflammation, is rare, and thank goodness it is rare. What happens with anaphylaxis, if you remember, there's systemic inflammation, blood vessels vasodilate, vessels get leaky and fluid leaves and enters tissue. So there's a reduction in blood volume and therefore a reduction in blood pressure. And if blood pressure drops enough sufficiently, then somebody goes into anaphylactic shock. Now, when you think about it, I want you to look at this word here, adjuvant. Now, vaccines often contain adjuvants, and adjuvants are chemicals such as aluminium that will boost the immune response. Now, adjuvants have been used for like 70 years, and they are very safe to use in vaccines. But in some people, follow me on this. Let's say as a baby, your mother or father took you to the doctor to have a vaccination, and there was a particular adjuvant in the vaccine that you got. Okay, in some people that can prime the immune system to produce those preformed IgE antibodies. Remember those from the immediate hypersensitivity recording? Then let's say they take that baby back, or take you back for a subsequent vaccination 6 months to a year later. And if that adjuvant is present in that same vaccine and their immune system has been primed, then there will be a bigger immune response to that adjuvant, and you'll get that sort of mast cell degranulation from that preformed IgE. And then if that adjuvant is in some more subsequent vaccines, then that reaction is going to get stronger and stronger over time, and unfortunately it does lead to anaphylaxis in some people. There are other allergic reactions to egg contents of some vaccines in some people. Also, gelatin is in some vaccines as well. Now, historically, multi-dose vials were used as well, and preservatives were added to the vaccines to stop, microbial growth inside the liquid itself. And historically, a derivative of mercury was used, but this is no longer done. Okay, so what I want to sort of press home is, that it's not unusual to have a very mild hypersensitivity reaction to the components of a vaccine, but anaphylaxis is rare. It is due to that preformed IgE antibody. And so, it's often to these adjuvants rather than to the targeted antigen itself. Okay, so just wanted to show you this table here. I think maybe you saw it last year too. I don't know, but it's no problem seeing it again. Here we have the number of deaths from currently vaccinated diseases in Australia between 1926 and 2004. All of the red boxes are the last decade before vaccination. Then we have the pale blue, which is the commencement decade of the vaccination. And then the green is the first full decade of child vaccination. Okay, so let's have a look at it in terms of these 5 diseases here: diphtheria, whooping cough, tetanus, polio, and measles. All right. Okay, here we have for diphtheria in pale blue, the commencement decade of vaccination was between 1926 and 1935. And you can see about 4,000 deaths here for diphtheria in that time. In the first decade after vaccination, you can see a sudden drop down to 2,800. And then in all of the decades after that, we're getting less and less deaths. Amazing, amazing. Similarly for whooping cough, here we have between 1926 and 1935, the last decade before vaccination. All right, so about 3,000 total deaths there. Big drop in the first decade after vaccination. In the commencement decade of vaccination, and then a massive drop in that first full decade of child vaccination. And then that's continued to drop, and now very few deaths from whooping cough. And you can follow these all yourselves. You can see that tetanus, again, massively successful, that vaccination program. Look at polio, like it's just incredible, going from 1,000 deaths in just after the Second World War, and then a massive drop to virtually no deaths at all. And then the same with measles vaccination programs too in children. Now, some vaccinations do target viral infections that are known to cause cancer. For example, human papillomavirus, or HPV, which is the cause of most cervical cancers. Now, here in Australia, a vaccine was developed called Gardasil against human papillomavirus, and I'm sure that most girls in the class and even most boys at this stage have had their Gardasil vaccinations. This is done very early in teenage years, and that's because the human papillomavirus is transmitted via sexual intercourse. So by vaccinating girls early, before they become sexually active, then they will develop that memory to HPV, so that then when they do become sexually active, their immune system can respond pretty quickly if they are exposed to HPV, and that HPV can be destroyed before it does any DNA damage at all, which might lead to cervical cancer. And of course, boys are also getting vaccinated with Gardasil to prevent transmission of the human papillomavirus to begin with. Okay, everyone, what I thought I'd do is just show you a couple of slides on the various sort of COVID-19 vaccines that are currently being rolled out in different parts of the world. Firstly, starting with these next generation vaccines, which are these messenger RNA vaccines. I'm sure many of you have heard of the Moderna vaccine and, of course, the Pfizer messenger RNA vaccine. Okay, so these two are very similar. They sort of differ a little bit in how they're stored, but for the purpose of this, they're very, very similar. So they're both encapsulated messenger RNA vaccines. So they contain a sort of a code that will code for the spike protein of SARS-CoV-2. Okay, so that's administered. So this messenger RNA is administered or protected in a lipid nanoparticle, much like a soap bubble. Okay. Once then absorbed into the cell, that messenger RNA then starts to express the spike protein. And the spike protein then will cause our immune system to respond and to produce an adaptive immune response to that spike protein. So both a T cell response and a B cell response. You can also see that it's the same sort of response here for the Pfizer vaccine. All I'm going to say about vaccination, and now just finishing up on this recording very quickly with anti-serums and anti-venoms. So remember, with vaccination, you're putting an antigen into somebody to stimulate an immune response. Here with anti-serums, you're introducing an exogenous antibody, and with an anti-venom, you're introducing an exogenous anti-venom. Okay, so this might be done if somebody with an anti-serum, for example, if somebody has been infected with a very serious pathogen, so that causes a very severe illness, and maybe their own immune system can't fight it. And remember that primary immune response takes time, and if the illness is severe enough, they may die before the primary immune response, is actually effective. So you could give somebody an anti-serum in this case, so exogenous antibodies, to rapidly stimulate an immune response against a known pathogen. Antivenoms are purified antibodies to a particular venom or toxin. So let's say you've been bitten by a snake. You might be given one of these antivenoms, which are antibodies to that snake bite toxin. And those antibodies bind to the toxin to inactivate it. And again, they're given, so the antivenom is given because there's literally no time for, to wait for the immune system to produce antibodies. So these anti-serums and anti-venoms are often produced by vaccinating large animals like horses or donkeys with the toxin or a part of the pathogen. And that will stimulate their immune system to produce memory B cells and then plasma cells and then antibodies to that particular pathogen, if it was a pathogen, or to the toxin. Then the blood of those, their blood is collected from the horse or the donkey, and the antibodies are harvested from that blood, then to be used either in an anti-serum or as an anti-venom. So I've just got one little final question for you, and that's anti-venoms can usually only be used once. Why is this? And there's a hint there, you are putting an animal antibody into a human. So have a think about that for 10 seconds. It sort of relates to everything that we've been saying. So here you're putting an animal protein, so something foreign, into a human. Okay, so that the human then will be sensitized to that foreign protein. So that then if you administer that same anti-venom again, there could be a serious allergic reaction on that second dose.